Okay, so we are still looking at kinetic proofreading. So let me draw the scheme here on the board. So once more. So here we have this delay. And then we can make correct product. The alternative route is identical. However, B, the lifetime of the EB complex, is shorter than the lifetime of the EA complex, such that if you wait longer before you do the catalytic event, more B will have fallen off than A. So the net effect is going to be that you accumulate EA. And that's what we want to show. Alright? So we define again the error fraction, which is k cat prime times E star B. Okay, so k cat prime, kr, k plus, k minus prime, k plus, k minus, kr, k cat. Okay, so that's going to be the notation for our kinetic parameters. So then the error fraction is the rate of incorrect product formation over correct. So we need to determine what E star B is, right? And let me check one more thing before I continue. We also need to give this reaction a name, so that's K4 prime. Okay, so so first we need to figure out the E star A and B concentration. We're going to do that at steady state as we did before. So we need to write down the balance for E star A. Yeah. So that's going to be KR times EA minus K4 times E star A minus K cat times E star A. Yeah. So that means that E star A equals KR times EA K4 plus K cat. Yeah, and that's going to be at steady state. Yeah, alright. And we also need to write down what E star B is. Right? That is the steady state concentration of EB. K4 times A star B minus K cat prime is also a prime, I guess. A star, oh, the same. Yeah, it's a prime. EB as a 0. So E star B as of course the same sort of logical structure as the previous equation. Right, okay. So now the problem we're left with is that we need to figure out what EA and EB is. EB is right, we're going to do this at steady state. Right. So that means that A is at steady state. KR, and we need to write down the balance for EB. So that EBS is right? And so now we know this guy, that's that guy, so we can substitute that. Multiplied by k plus times es times a, k minus plus kr, and here we have the same. Okay, so now we have the equations for the starch species, so the energized enzyme complexes, in terms of parameters and the steady state enzyme concentration. So now we can substitute those. So you probably need some more space, so that divided by k cat. So first E star B equation, so that is kr divided by k4 prime, k cat prime, k4 times es times b, k minus prime plus kr. So this I have to divide by the equation for EA, so that's the same as multiplying its inverse. So let's do that. Okay, so let me now remove the other equations, then we have a look at the final equation. Alright, so now we have the error fraction equation, and what the only thing left to do is now that we should simplify it. So again we say A equals B, because otherwise we don't have an honest comparison. Having more B will always lead to more incorrect product formation after all. And we're going to assume that the k cats are the same. This is away. And also the, I'm not sure whether the exit rates are also assumed the same, I guess not. ES disappears. ES disappears like this. And now we have two catalytic rates, right? So we have catalytic rates, constants. That's KR and KCat. And in order to minimize the error fraction, it turns out that Kr should be much smaller than K minus, and also much smaller than K minus prime, and the same for the Kcat. So we assume that these binding reactions, so having to do with K plus and K minus, those binding reactions are way faster than the catalytic reactions. Okay, so that means that we can throw this away, right? So because this is negligible with respect to K4 minus, right? And because K4 minus is also one of these K minus events, right? Because it's a dissociation reaction of A. So the other thing that we're going to do, K4 minus is K minus. So K4 is K minus, and K prime is K minus prime. So that's going to be K minus prime. Okay. So that's that, and then this is negligible. That disappears against that, and that's also negligible. And then what we get is, and this is K minus. So effect what we get is the error fraction equals k minus divided k minus prime squared. Okay. That means that k minus, now we can divide it by k plus, right? If we also divide the lower, the denominator of this ratio by k plus, this is the same. And then you get ka divided by kb squared. So what turns out is that if we make these simplifying assumptions, so again we say, look, the concentration of A is going to be equal to B. As soon as the complex is formed, the k cats are going to be identical. The exit reactions, so this is an A exit reaction, that's the same as this exit reaction, so a dissociation reaction of A. Here you have another dissociation reaction, but then of B, and these are identical if we assume that. And if we also want to minimize the error fraction, that then means that the catalytic rate constants are a lot slower, so smaller in values than the binding constants. And if we do that, then the error fraction eventually equals Ka divided by Kb. Whereas the error fraction, so no proofreading, right, was Ka divided by Kb. Now, so that means that the error fraction has decreased, yeah, because it was already smaller than 1. So multiplying with it and taking it squared will even make it even more smaller. And the other thing that turns out, if we would have added another delay, yeah, so this is 1 plus n, where n is the number of hydrolysis reactions. So it turns out that if you add one more delay reaction, it is to the power 3. If you add 3 delay reactions, it's to the power 4. Okay? So adding more and more delays increases the error fraction. Yeah? And why is that? Well, per delay step, more B is lost than A, so there is a net accumulation of A. So another delay step will even more and more and more. But if you have more, then of course the concentration of A also decreases, but less than B. But that means that if you have more delay reactions, that eventually the flux of product formation, which is K cat times this, right, that guy, this product, so this flux, yeah, if you would plot that as function of the number of delay reactions, this flux goes down, yeah, but the error fraction, so they say the correct product fraction, which is 1 over the error fraction, increases. Okay, so the flux goes down, so the performance goes down. Yeah, so in terms of how many copies you make per unit time, you get more and more of the right copies, but at an ever lower rate. Okay? So that means that the evolutionarily optimal process is somewhere in the middle. Okay? So it's going to be somewhere with a certain number of these delay reactions, but not too many to decrease the flux, and not too few, because otherwise you may have a high flux, but then you make too many incorrect products. Okay, so this is the essence of kinetic proofreading. Due to energy, the energization of a protein, by which you delay the catalytic event, you can accumulate the right product, because the right molecule will have a longer lifetime to the protein than the other, the incorrect one. Okay, and the exact explanation for how the ratio of this changes with time, right? So how the ratio of the correct guy over the incorrect guy, how this increases with time due to the fact that you add a delay, is found in the syllabus, but it's not exam material, so I'm not going to explain it here, but it's certainly interesting to have a look at. All right, thank you.